In this last video on analytical geometry, we are going to look at quadrilaterals. Now, first of all, we're going to look at the properties in the proof. So we're basically just going to go through the summary of that. And then we're going to look at how to apply the distance, the midpoint, and the gradient formula when we do proofs. And then we're going to look at some real examples. Now, if we start off with a parallelogram, we have 5 options that we can choose from to prove a parallelogram. So the first one is you prove both pairs of opposite sides parallel, or you can prove both pairs of opposite sides equal, or you can prove that both pairs of opposite angles are equal. You can also prove that one pair of opposite sides are equal and parallel, or finally you can prove that the diagonals bisect each other. Alright, so you don't obviously have to prove all of these. When you are asked to prove a parallelogram, you pick one that suits what you've been given, and then you go ahead and use that one to prove that it is a parallelogram. Okay, now next up is a rhombus. So we've got 2 options. So you can prove that the quadrilateral is a parallelogram, so meaning picking one of the previous ones, and then additionally also proving that one pair of the adjacent sides are equal. Or you can prove that it is a parallelogram and that the diagonals bisect at 90 degrees. Meaning the lines, the red lines, basically cut each other in half at an angle of 90 degrees. Next, we've got a square. So 3 options. We can prove that the quad is a rhombus with an angle equal to 90. Or you can prove that the quad is a rhombus with equal diagonals. Or you can prove that the quad is a parallelogram with one angle equal to 90 and a pair of adjacent sides being equal. And then for a rectangle, one of 2. So prove that the quad is a parallelogram with an angle of equal to 90. So only one of the angles you need to prove equal to 90. And then you can prove that the quad is a parallelogram and the diagonals are equal. And then a kite, there's only one. You prove that both pairs of adjacent sides are equal, and with adjacent sides we mean that the sides next to each other. So you prove this side is equal to this side, and you prove this side equal to this side, and then you say that it is a kite. And finally, the trapezium, you can basically just prove that one pair of opposite sides are parallel. Okay, so those are the proofs that you need to know, what to prove for what quadrilateral. Now let's look at how to do it using the distance, midpoint, and gradient formula. So I'm going to start with a simple question of how do I show that 2 sides are equal? And when we look at the parallelogram, we can see from the second proof that you need to prove both pairs of opposite sides equal. Now, the answer to that is obviously the distance formula, because that gives you the length. And then if you have the 2 distances the same, you can say that they are equal, and then you've done your proof. So if we name our parallelogram ABCD, basically what we'll do is to find the distance of AB, we substitute that in the distance formula, and we take the opposite side and we find the distance of that side, DC, put it in the distance formula, and then we can conclude that AB is equal to DC. And we've concluded our proof by just then also adding that ABDC is a parallelogram. And then how do I show that 2 sides are parallel? So again, if we look at the parallelogram, the first proof over here, we need to prove that both pairs of opposite sides are parallel, and the answer to that is the gradient formula, because we've seen that with the gradient formula, if the gradients of 2 lines are equal, then it means that the lines are parallel to each other. Now, once again, if we name our parallelogram ABCD, we can start off and just calculate the gradient of AB, the one side, and then calculate the gradient of DC. So we've calculated the gradient of both of them, and then we can see, or if it is a parallelogram, obviously, then it will show us that the gradients are equal, and then we can state that if the gradients are equal, then therefore the lines AB is parallel to DC. So the next question is, how do I show that 2 lines are perpendicular? Now, when we have to prove the rhombus, for example, in one of the proofs, it shows that we need to show that the parallelogram and the diagonals bisect each other at 90 degrees. Okay, so we basically need to prove that the diagonals are perpendicular to each other. And the answer is again the gradient formula, because we know that if we have the gradients of two lines and we multiply them together, and that gives us -1, then it means that the gradients are perpendicular. So again, I'm going to find the gradient first of the one diagonal, and then going to find the gradient of the second diagonal, dB. Then I'm going to multiply the two together, and my answer should come out as -1 if the diagonals are perpendicular to each other. And when we do that, we can say, therefore, AC is perpendicular to dB, and hence we've proven that the two lines are perpendicular. And then a final question, how do I show that two lines bisect each other? So again, when we look at the parallelogram for an example, we have to prove, in the final proof, you have to prove that the diagonals bisect. In other words, they cut each other in half. And the answer for that is the midpoint formula. Now, in the midpoint formula, we can again name our our quadrilateral ABCD. And then what we can do is to find the midpoint first of AC, and then find the midpoint of BD. So basically finding the midpoint of these two diagonals. And if the midpoints are the same, so if we can show that the midpoint of AC is the same as the midpoint of BD, that basically means that the lines cut each other on the midpoint, which then tells us that they half each other, they cut each other in half. All right, so then we can just conclude that AC and BD bisect each other. Okay, so that was just a practical approach of, how to prove parallel, perpendicular, equal, and to how to prove that lines bisect each other. Now let's look at applying these principles in the actual examples. So for example 1, we have to prove that the quadrilateral ABCD is a parallelogram. Now, when we look at the summary of proving parallelograms, we can choose one of the 5 options. Now, we have to look at what does the given diagram look like, what information was given to us in this parallelogram, and then with that decide which one are we going to use or can we use. So we can definitely prove both pairs of opposite sides parallel, because we can find the gradients. We've got the coordinates of all the points, which means we can find the gradients of all these lines. Okay, and therefore we can basically show that both pairs of opposite sides are parallel. Or we can just find the distances of all the lines and then show that the opposite sides are equal. Now, for the third one, prove that the opposite angles are equal. That would not work in this case because we do not have the angles. It's in grade 11 it will be possible to find it, but also not very practical because it's a long way. But for now, this will not be possible in this question. And then for the fourth one, prove one pair of opposite sides equal and parallel. So that's also possible. We can find the distance and the gradient of two opposite sides and show that they are parallel and equal. And then for the other one, prove that the diagonals bisect. Now, basically finding the midpoints of BD and AC. It's possible, but I wouldn't recommend it if they haven't drawn the diagonals. So if the question, like if the line segment isn't in your diagram, I would rather use a different method where the lines are given. If there's no other option, then go for it, but work with what is given, because that is kind of a guide of what you need to do. So, like we've seen here, either one of the green ones would be possible, okay? And now, how to decide which one to use? At the end of the day, it doesn't matter, but we always want to do the less amount of work to save time, okay? So, in each of these cases, I think they're basically the same, but I think maybe the gradient will be the shorter one. So, I'm actually just going to make it interesting, use the third one, to take one and to calculate both the distance and the gradient for the opposite pairs. Alright, so let's get started with that. So I'm going to start with the distances. Now, also just to save space, I'm not going to write out the formulas. So we've got AB is, now for the distance formula, we know that it is, actually let's write it once, because that would help us with the substitution. So we know that the distance formula is then the x2 minus x1 squared plus y2 minus y1 squared. And then we can just substitute those values in. Okay, let's maybe do this. I don't know how much space we're going to need. All right, so let's substitute it in here. So we're going to choose AB, and then we've got, for the x values, let's start with this one. We'll say minus 5 minus negative 12 squared plus, and then for the y values, 12 minus 8 squared. Right. And then we can just calculate that. So we can put this in the calculator all at once, but I like to simplify the inside first. So we've got minus 5, this becomes a plus. So minus 5 plus 12 is 7, and 7 squared is 49. And then plus the 12 minus 8 is 4, and 4 squared is 16. So 49 plus 16. And then if we put that on the calculator, square root of 49 plus 16 is equal to 65. Square root of 65. Okay. Next, let's look at the distance. So now we want to do the distance of DC. So DC is equal to the square root. Let's just substitute in. So the x values, we've got 11 minus 4 squared plus, and then the y values, minus 2 minus negative 6 squared. And we're taking the square root. Okay, so this then simplifies. This is 11 minus 4 is 7. So 7 squared is 49. And then minus 2 plus 6 gives us positive 4. And positive 4 squared is 16, so plus 16. All right, so now you can see, once again, we just have like the 49 plus 16, so we can just write, okay, this is also the square root of 65. Okay, that's done. Now I want to find the gradients of both of these sides. So the gradient of AB, and the gradient formula is the change of y over the change of x. Okay, and then we substitute that in. So the gradient of AB is 12 minus 8, the top, over minus 5 minus negative 12. And then simplify. So this is 4. And this is negative 5 plus 12. So that becomes 7. So 4 over 7. Okay, and then for the gradient of DC, we have change of y over change of x. Ooh, this was wrong. This is 2, 1. At least our substitution was done correctly, so that was just the formula. Okay, and then we substitute. Now, DC, so minus 2 minus negative 6, the y values. And then 11 minus 4. Okay. So minus 2 plus 6 gives us positive 4, and 11 minus 4 is 7. Now, from this, we can see that the gradient of AB is equal to the gradient of DC. Okay, we can therefore conclude from this that AB is equal to DC, okay, with our distances, and from this we can say that AB is also parallel to DC. And therefore, so we can just state the proof that we've just done. So like just write it down in words as on the summary. So you can say that one pair of opposite sides are equal and parallel. So therefore, we know that ABCD is a parallelogram. And then we're done. Now, in example 2, this is not a proof, but this is actually a question that I've seen so many times in past papers, ranging from grade 10 to grade 12. This question is a very common question. And it says that EFGH is a parallelogram with vertices E, F, G, and H. Okay, determine the coordinates of H. Okay, now basically, first of all, let's just do a rough sketch because the order in which we're going to do it is important. Now, there's more than one way to do it, but I'm going to obviously explain the way that I think is the fastest and the easiest to understand or to do, and this is just the way that I always do it. So E, let's just see where they lie roughly. We don't have to know exactly, just to roughly see where they lie. So E is like -2 and 2, so normally like more or less there. And then F is like 1 and 8, so more or less there. And then we've got 3 and 5, so that's 1, got 3 and 5, more or less maybe there. Yeah. G. And that leaves us with H. Okay, so we don't know where H is, but if we're given that it's a parallelogram, we can kind of see, okay, what's going to form our parallelogram. If the point must be like somewhere around here. Okay, so let's just write in our coordinates, because that's going to be easier, make our calculation easier. And then F is 1 and 8, and G is 3 and 5. Okay, and this is X and Y. Now, what I'm going to use is the fact that from a parallelogram, I know that the opposite sides are equal to each other. Okay, now if we break it up into its X and Y coordinates, if the opposite sides are equal, then like from F to G is equal to E to H. Then and it's a parallelogram, so they also run parallel to each other. So that's actually very important. What will happen is the change of y's from F to G will also be the same as the change of y from E to H. Okay, and the change of x from F to G will be the same as the change of x from E to H. Okay, so I'm going to basically break my x coordinates up and my y coordinates and calculate for these two separately. So to substitute that in, I'm going to say that that the x value of f minus the x value of g, so that's basically the change of the two, or the difference of the two, is equal to, so I started from the left-hand side to the right-hand side, so on this side I'm also going to start from the left-hand side to the right-hand side. You can do it the other way around, that's fine, as long as you do the same direction for both. So from E to H, the x value of E minus the x value of H, and then substitute in those x coordinates. So it's basically going to be 1 minus 3 is equal to minus 2 minus x, and then I'm just going to solve for x. So x goes over to this side, and then we have minus 2, and then I'm going to take the 3 over, that becomes plus 3 minus 1. So x is then equal to 0. Okay, so that worked out to be 0, meaning our coordinate actually lies like on somewhere on the y-axis. Okay, now let's do the same for the y value. So let's say the y coordinate of f minus the y coordinate of g is equal to the y coordinate of E minus the y coordinate of H. So basically we're going to take the y values. We've got 8 minus 5 is equal to these y values, 2 minus y. And then we just solve for y. Very easy linear equation. So y goes over to the left-hand side, and our constants comes over to the right-hand side, just changing sign. And then we have 2 minus 8, which is negative 6, and then plus 5, which is then negative 1. So y is negative 1. Right, and that is our coordinate. So we can just then, and very important, they say determine the coordinates. Okay, so if they ever say give the coordinates, you don't just end by the x and y values. You have to give the coordinates, which is the h value with 0 for x and minus 1 for y. Okay, now for example 3, show that JKLM is a rectangle. Now let's look at how do we prove a rectangle. So first of all, you can prove it's a parallelogram with angles equal to 90, or you can prove that it's a parallelogram with diagonals equal. Now, in this case, we just need to think a bit about like what's going to be the shortest way, because we've seen like the parallelogram proof in itself is kind of long. So now we have an additional thing, like we have to prove the parallelogram and additionally like prove either that the angle is equal to 90, one of the angles is equal to 90, and or we have to prove that the diagonals are equal. So let's go with the first one. Well, actually no, let's just talk about why. Now, when we want to prove that an angle is 90, what do we need to do? We need to find the gradient to prove something is perpendicular, right? We need to show that, or we need to calculate the gradients, all right? So if we look at like the parallelogram, where actually can we also use the gradients, or if we basically show that both pairs of opposite sides are parallel, we are also going to calculate the gradients of all the lines, okay? So that means that I wouldn't have to do double work. Like let's say I used the second one, then I'd have to find the distances of all the sides, and then when I move back to proving the rectangle, I'll have to find the gradients as well. So I would rather go with proving the parallelogram by the first method, because then I just need to calculate the gradients of all the sides, and then it's already calculated, so then I can easily just prove that the two angles are or that one angle is also equal to 90. Okay, let's just jump into that. So I'm just going to go straight ahead and find the gradient. So gradient of JK, let's just start with JK, is equal to, so we've got JK is equal to the change of y, so it's 8 minus 5 over minus 2 minus 3. So this is going to be negative, or this is going to be 3 over negative 5. So it's going to be negative 3 over 5. Then let's prove the find the gradient of ML. So the gradient of ML is equal to minus 2 minus negative 5 over negative 8 minus negative 3. So negative 8 minus negative 3. Right, then if we substitute that in, or if we calculate that, minus 2, that becomes plus 5. So basically we've got 3, and then this is minus 8 plus 3, so that's negative 5. So it's going to be minus 5. So negative 3 over 5. Okay, next let's look at the gradient of Jm. Okay, so the y value is 8 minus negative 2. And that is then over minus 2 minus negative 8. So minus 2 minus negative 8. Okay, let's simplify that. So this is 10, 8 plus 2. And this becomes 6 because it's minus 2 plus 8. So that is 6. And then this then simplifies to 5 over 3. So 5 over 3. Then for the gradient of the final gradient, so the gradient of KL, is the y values 5 minus negative 5, and then that is over 3 minus negative 3. Okay, and then we've got 10 over 6, and that simplifies again to 5 over 3. Right, so now I've done all the calculations that's needed. So we can start off and say, okay, the gradient, you can see that the gradient of JK is equal to the gradient of ML. So JK and ML. So the gradient of JK is equal to the gradient of ML. So this means that JK is parallel to ML. And we also know that the gradient of Jm is equal to the gradient of KL, these two. So that means that, so therefore, Jm is parallel to ML. All right. So now we can say that we see that both pairs of opposite sides are parallel. So therefore, JKLM is a parallelogram. So the first part is done. Now we need to prove that one of the angles are equal to 90. So let's say that one. And now to do that, we're going to say what is the gradient of ML. We take the gradient of ML multiplied by the gradient of KL. And we substitute that in. So ML is -3/5 multiplied by KL. So that is multiplied by 5/3. And the 5's cancel, the 3's cancel. This gives us -1. So therefore, we know that ML will be perpendicular to KL. And therefore, we can say that that the what do you call this, a quadrilateral. So we can say quad is a parallelogram. And remember, I'm now just writing one of the proofs that we saw in the what do you call it, the summary. So the quad is a parallelogram with angle equal to 90. With angle equal to 90 degrees. And then we can say, therefore, JKLM is a rectangle. And that completes our proof, rectangle. Okay, then we're done with this one. All right, so now for the last one. Show that NOPR is a rhombus. Let's look at the rhombus and how to prove it. So we have one of two options. We can prove that it is a parallelogram and one pair of the adjacent sides are equal, or we can prove that it is a parallelogram and the diagonals bisect. So we basically just want to decide which one's going to be shorter. Now, when we prove that the parallelogram it's parallelogram and one pair of the adjacent sides are equal, how to prove the parallelogram, you can go about anyway, but obviously it will make sense if you prove it that both pairs of opposite sides are equal, because that means to use the first proof, you're going to basically find the distance of all four sides, and then you've basically proved that it is a parallelogram by showing the opposite sides equal. And then when you have to prove that the adjacent sides are equal, you've already have calculated the distances, so then you can just show that the adjacent sides are equal. Okay, so that's one option. And then the that the diagonals bisect at 90. All we need to do for that is just show, prove that the gradients, when we multiply them together, they will give us -1. Now, what will we use when we prove the parallelogram for that case? I would say also any one, but we can focus on the diagonals. We can first prove that they bisect by basically finding the midpoints, okay, and then going back to the rhombus and just ending up by proving that it is at 90 degrees. So I'm going to do that method. To first just prove, because proving that the diagonals bisect is both proving that it's a parallelogram and that it will complete our proof for the rhombus, and then you just need to find the gradients to prove the 90 degrees. Okay, so let's start with that. So first thing I need to do is to find the midpoints. So let's just write the midpoint formula here, because I want to save space over here. So the midpoint formula is going to be x1 plus x2 over 2, and then y1 plus y2 over 2. Okay, so adding my x coordinates, dividing it by 2, and same for the y coordinates. Now the midpoint of NP. Okay, so just to write the coordinates, 3 plus -1 over 2. And for the y values, 9 plus -3 over 2. Okay, so this is then 2 over 2, because that just becomes 3 minus 1. So it's 2 over 2, and that gives us 1. And then 9 minus 3 is 6. 6 over 2 is 3. Okay, that's our coordinates there. And then midpoint of RO is equal to the x value is minus 2 plus 4 over 2, and the y value is 4 plus 2 over 2. Okay, so minus 2 plus 4 gives me positive 2, and 2 over 2 is 1. And then 4 plus 2 is 6, over 2 is 3. Okay, so here we've seen that the midpoint of NP is equal to the midpoint of RO. Now, therefore, I can say that the diagonals bisect. So, therefore, NP and RO bisect each other. Okay, so therefore the quadrilateral NOPR is a parallelogram. Okay, now we've proven it's a parallelogram, so the only thing that's left is just to prove that they actually bisect at 90 degrees. So to do that, we're going to find the gradient. So gradient of NP, the change of y over the change of x, so we've got 9 minus negative 3 over 3 minus negative 1. Okay, and this then is 12, so 12 over 4, so this is 3, and then the gradient of RO is the change of y, so 4 minus 2 over the change of x, minus 2 minus 4. Okay, and this is 2, and this is minus 6. So 2 over minus 6, and that simplifies to negative 1 over 3. Now I'm going to multiply the gradients together, because to prove that two lines are perpendicular, we have to use the formula. So gradient NP multiplied by gradient of RO is then equals to 3 times negative 1 over 3, and the answer there is negative 1. Okay, so therefore we know that the lines NP is perpendicular to RO. So now I'm just going to state what is in the proof. So it is a parallelogram, so the quad is a parallelogram with diagonals, bisect at 90 degrees. Okay, and therefore we know that NOPR is a rhombus. Okay, so that is our proof. Right, then we've done all the examples and we are done with this lesson.